Okay, so I guess is it working or working? I have no idea. Speaking. Yeah, looks like it's working. Okay, so we did case one, which is to say that all the bending was resisted by the flanges. Case two, we're going to do today, which is to say the panel or the skin, so let's say the panel is effective in resisting bending. Okay, so to save some time, I'm not going to go and redo the figure. Let's see if I can. Oops. See the notes from yesterday. Okay, so we're dealing with this problem over here, okay? There was a general procedure, so this was the problem we're doing, case one, okay? So if we do case two, if you look at the notes, so go back to your notes and look at it. Case one was this. Case two, we need to calculate the stresses given by this complicated equation. So this will be the step one over here, okay, for case two. The panel is fully effective in resisting bending. And what are we looking for is that before we had Q equal to constant, now we need to find the shear flow will not be constant, will not be constant, will be some type of in function of S, okay, as you will see at the end. Okay, so we're going to do step one, calculate the load PC1, calculating the stresses. Then we do step two, find P1, P2. That's completely unchanged as before. Probably I will just show this figure again. All right, to have it over here. And then determine the shear force in the panel. This step will be the same. But once we go to step four, instead of finding this constant value, we'll use this expression to find what will be Q. All right, so here we go. All right, so you know which one we are solving. So for case two, we have step one. We use the equation PC1 equal to sigma bending stress 1 times B1. PC2 will be equal to the bending stress at 2 times B2. Okay, so from previous notes, okay, we found that IXY was equal to 0. MX equal to 20 kilonewtons meters. And I don't have it with me. Okay, and then we'll see what happened with IXX. Okay, so for IXY equal to 0, and Y equal to 0, okay, the bending stress equation reduces to what? We have sigma Z will be equal to mx y divided by IXX. Okay, so now this is something that is sometimes is done, Sometimes it's not done, it's not that important, but I like to do it so at least you see the difference. All right. Is that now we're gonna say we're gonna use the I. We're gonna calculate IXX. We're gonna have IXX due to the flanges plus the IXX due to the panel or the skin. Let me just call it panel over here. So if I do the figure over here, this is our B1, B2. We had right in the middle the neutral axis. We have here the Y. We know thickness of the panel here is T. Then what did we have? If you remember, this is at the cut. So at the cut at the section, we had here H equals 0.3. Remember, this is the section A prime. Okay, so here I can say where I flanges, IXX flanges, the one we did before, will be equal to what? Y squared dA, which is the summations of the Y sub R's square B sub R. So in this case, we're gonna get Y1 squared times B1 plus Y2 squared times B2. And if you do this calculation, you get IXX flanges equal to 18.6, no, 18, 10 to the 6 millimeters to the 4. Okay, what would be Y sub 1? Y sub 1 would be 0.15, no? One, let me put here, Y sub 1 would be equal 0.15, Y sub 2 negative 0.15. Okay, the next will be IXX skin panel. 18 times 10 to the 6 millimeters to the 4. I can maybe try to zoom in a little bit to help you. All right. But then if I go out of screen, let me know. So here the giant expression would be 112 T H cube. Remember the moment of inertia of this here, let's say this is AB, is I equal 112 AB cube, okay? So here the base will be A is A and B is H cube. So in this case, this is going to give you 112 times 2 millimeters times 300, which is the height. I do this in millimeters cube. And this is going to give IXX panel equal to 4.5 10 to the 6 millimeters to the 4. So what do we have at the end? So that the total moment of inertia, the total area moment of inertia is what? IXX would be equal to IXX flanges plus IXX panel. This is going to give you an IXX of 22.5. I guess I forgot the 10 to the 6 on my original notes. Then to the 6 millimeters to the 4. Okay, so why did we do all this stuff? We did all this stuff to calculate the bending stress at each one of the locations. So we come over here. All right, so let's say now substituting into PC1 equal to sigma Z1 times B1, PC2 equal sigma Z2 times B2. Okay. And so this would be one equation, and the equation we have is sigma Z equal mx times y divided by IXX. We just said before that what? Mx. So let's put here where B1 equals B2, I think was equal to 400 millimeters square. Mx we say was equal to 20 kilonewtons meter, so that would be what? 20 10 to the 6 newtons millimeter. And IXS we just calculated to be equal to 22.5 10 to the 6 millimeter fourth. Okay, so if we do the first one, sigma Z1 will be equal to what? Mx times y divided by IXX. So if I do here again a new figure, so this is B1, B2, neutral axis, y. That distance here was h equals 0.3. Okay, so what do we get? We get 20 10 to the 6 times what will be y in this case. So this is 0.3, so it should be 0.15 meters, which will be a what? 150 millimeters. So this is okay, but in millimeters. All right. This is the y sub 1, y sub 1 equal to 150 millimeters. Y sub 2 will be minus 150 millimeters. All right. Divided by IXX, that we say is 22.5 10 to the 6. So if you do this calculation, you get 133.33 newtons per millimeter square. And similarly, we do sigma Z2 will be equal to mx y sub 1 IXX, y sub 2. This will give you 133.33 newtons millimeter square. All right, here let's be careful. So here we go. So this is our problem that we are solving. So look here at the board. If you pull this down, the top will be in tension or compression. This side will be in tension, this one will be in compression, okay? So if you want, that's why I don't pay that much attention to the signs, but if you want, the top side will be in tension, so if you want, you can put here tension, or leave a positive value, and here put a negative value, and put here compression. I don't like the value, the positive negative value, I rather write tension or compression. Okay, so we have this, and let me put this way, and then we have P Z1 equal to sigma Z1 times P1 will be equal to what? 133.33 times 400. This gives you PC1 equal to 53.333 10 to the 3 Newton, and PZ2 will be equal to sigma Z2B2, okay, will be to 53.333 10 to the 3 Newton. Yes. So this stuff was step 1. Okay, if you look at the notes, tell me what should be now step 2. This one should be common. I think it should be, if I'm not wrong, determine P1 and P2, is that correct? But I want you to go and check your notes, okay? Okay, so I think you should have here from the equations that PY1, perfect, is equal to PC1 times tangent alpha 1 equal PZ1 delta Y sub 1 delta Z sub 1, and PY2 equal to PZ2 tangent alpha 2 equal to PZ2 delta Y sub 2 over delta Z sub 2. Okay, so from the previous example, I'm not going to redo it. Remember this the step I told you that's doing this figure, okay? We see that tangent alpha 1 will be this height against this length, okay? And we calculated this to be equal to 0.05 for both of them. All right, here you have it. Okay, from the previous step 2. Okay, so basically we do the same thing. Camera, so this will be equal to 0.05. Okay, from previously, okay? Okay, so now I can just go and substitute into this equation. Okay, so that's, let's say here, I have PY1 equal to PZ1 delta Y sub 1 delta Z sub 1 will be equal to what? Will be equal to the 53.333 10 to the 3 times 0.05. And this gives you 2,666.66 Newton. And similarly, you can do PY2 equal to PZ prime 2 delta Y sub 2 delta Z sub 2. And again, this will give you the same thing, 2,666.66. Okay, then we're gonna do something if you want for the signs of all this stuff, but for now I leave with no signs. Okay, I think it's easier. All right, so the axial or in plane forces, loads P1 and P2 are equal to what? We're gonna have P1 equal to Py1 plus Pz1, each one square root. P2 equal Py2 plus Pz2 square, everything square root. So the first one will be, let's see, Py1 is equal to what? 2,666.66 square plus Pz 53.333 10 to the 3 square. And this will be not much difference since the Py is so small. This will give you 53.33 10 to the 3 Newton. And this will be 53.33 10 to the 3 Newton. Okay, so basically what you see over here is Py1 is so small compared to Pz1 that it can almost be ignored. So, but let's go back for a second and do a little bit of the figure over here, okay? If you want to be details for the sign. So remember we have here, this is the figure, all right? So I'm going to do this figure in small size. All right, here. Okay, so we have this over here. So what does that mean? Remember we say over here, if this is what we have, the top would be what? In tension. The bottom would be in compression. So if that is the case, what does that mean? If it's in tension, this will be P1. And if it is in compression, this will be P2. So, okay, so if you really wanted to be very accurate, you see here, for P1, the Pz, we have here Z, Y. The Z would be positive, so we have Pz1, we can keep it positive, and Py1 should be negative. So if you really want it to be accurate, we should put over here Py1 equal to negative, but you don't have to, okay? As long as you get at the end correct. If you don't put it, it's fine. Then this one will be what? Both of them will be negative, so we have Py2 will be negative, and Pz2, what is Pz2 here? Negative over here. Important, guys. We do it at the end. Here, what's important is to mention that P1 is in tension. And P2 will be in compression, okay? So this figure to determine sign of Py and P6. But again, that's not that important. All right, if you look at the notes, what is step 3? What is step 3? Okay, determine the shear force VP on the panel, okay?
Yeah, we need option 2.
Correct, so we're gonna do option 2. Perfect, I forgot about that. Option 2. All right, thank you. So remember for option 2, oops, okay. Maybe that's not such a good idea, but option 2, so I'm going to do in red the external. This is the Vy equals 20 kilonewtons. And for option 2, what did we say we're going to do? We're just going to say that this is being resisted by what? Py1, Py2, and Vpan. So we go over here, we do summation of external forces equals summation of internal forces. So we have Vy equal to Vp plus Py1 plus Py2. Remember, just look at the magnitude. So this is going to give us what? Vp equal to Vy minus Py1 plus Py2. Okay, magnitude, here the same thing, magnitude. Okay. So we get what? Vp equal 20 10 to the 3 minus, what was Py1? 2,666.66 plus 2,666.66. And this is going to give us V panel of 14,666.68 Newton. This is the shear force in the panel. Okay, and finally, what is step 4? Correct, so step 4, determine the shear flow Q sub S, and this will be our page 4. Okay, so if you remember, for I, X, Y equal to 0, Vx equal to 0, all right? I don't know if I have it over here. Okay, see what we did the other day. I'm looking at here. Okay, so the long equation, let's see over here if I can go back to the notes. This long equation here, okay, this long equation here, all right? This one over here, okay? For Vx equal to 0, Ixy equal to 0, reduces to Qs equal to minus Vp over Ixx times integral of YT ds plus the summation of the B sub r Y sub r. So this is, remember we said this is the effect of the panel. This is the effect of the flanges. All right, so let's do the figure. So if I do here, a figure, we have B1, B2. This will be the neutral axis. We know that from neutral axis, we measure the Y. Thickness of the panel T is 2. Okay, and now we need to be careful. We're going to start from point 1. This will be our S. And this is basically our H over 2 if you want. And H, remember, is 150 millimeters. Sorry, H over 2 will be 150 millimeters. Okay, so if I look at the figure, what would be Y? What would be Y in this equation from point S? If you did the assignment, this should be pretty easy. What would it be? You do the assignment for today, we go from here to here. What is the distance? What is it? We go from here down to the neutral axis. I don't know if you did the assignment for today. That's what you have to do all the time, no? H over 2 minus S. So then we have what? T will be equal to the 2 millimeters. And basically that's it. So we have here Q sub S will be equal to minus Vp over Ixx. Integral of what? H over 2 minus S times TdS plus B1 Y1. We start from B1 Y1. Okay, we start at point 1. So this is going to give us what? So if you do the numerical application, you get Q of S, if you want, will be Q12. It gives you, this is equal to, let's write it down, we have time. Minus 14,666.68 divided by 22.5, 10 to the 6 times the integral of 150 minus S times 2 ds plus 400 times 150. If you do this calculation, you get QS equal Q12 equal to minus 6.518 10 to the minus 4 times minus S squared plus 3000 S plus 60,000. Okay, we do like we have been doing here at S equal to 0. This is like the assignment. Q1 will give you minus 39.11 newtons per millimeter. And at S equal to 150, Q, if you want, will be at the neutral axis, equal to minus 53.78 newtons per millimeter. So if we do the figure, this will be the distribution. And basically, we do the top and the lower part will be by symmetry. The what? We did not assume x, y is 0, so we know it's symmetric. I mean, if you want, you can redo the same thing as you did the assignment. You can go from the neutral axis to Q2 and redo the calculation. In this case, I just did it a bit faster, okay? All right. So what is the whole idea? If you remember, let's see, on the first note, is over here, we say that if, see, for case 1, we found a constant Q. I think it was about 44, if I remember right. That's what we did yesterday. So we have, let's say we found what? Yeah, 44.43. We did the final element. Now we did for case 2. We found that it goes from 39.11, basically constant, to a value of 53.78. Okay, so let's do the final element of this case over here. All right, so open FEMAP. And when you're ready, just open the model from yesterday. Yeah, I already worked on it a little bit, so I mean, I want to open. I don't want to save. Okay, file, open, Wingspar 1. Okay, and do file. Do you have FEMAP open, all of you? Do file, save as Wingspar 2. That way we have a new model. And now, I mean, if you want, no, I don't want you to get. Go to results, all results, and delete it. Delete the results. All right. And then you go back to the groups and click on show for model. And if you want to resend the thing, Control A. Okay, so this is our model over here. Okay, so in this case, this is case 2. Remember, case 2 is the panel now is effective in bending. So when we use shear panel, basically you're just saying that the panels are just effective in shear and not in bending. So what we need to do here, go to model, go to property, and what we do is we need to create a property so that the panel can resist bending. So we go to property, new, and that new property which can resist bending is we select over here plate. Click on plate. What is the thickness of our plate? It's 2 millimeters. We put over here 2. If you want, put here panel t equal to, okay, as property, and click OK. And now cancel. Now, I don't remember exactly how to do this, but so now the idea is to change. You see here you have the shear, is to change these elements, replace this element by these ones. So modify object element property. Okay. Method ID is fine. So we go to ID 3. So select elements to update property. So we're going to select the ones in 2, but 2 over here. ID 2, see if it works. Okay. Select property to update. For update, we want to use 3. So that's not going to work. This is not working. Why is that? Okay. So cancel. We want to change these ones for these ones. So we're going to replace the shear property with the panel. So I don't know. I mean, let's see. Modify object element. Maybe let's go to type and see over here. Cancel elements. See here by type. Okay, shear panel. Okay. All right. So maybe that will work or not. Modify object element by type. Method. Type. Let's see. So type. We'll change the shear panel. Wow, this is pretty. I've never seen that. Shear panel linear. Okay. Yeah, but that's way too complicated. So you need a way to do this stuff. Why is not doing with properties? So modify object element. Why didn't it do with property ID? Let's try property again. What is it? Select update property. So let's say method, or maybe that. Okay, maybe it's this property instead of ID. So we're going to replace this one 2, but over here 2. Okay. Why is the thing? Select property for update. So you think that means the one we want to, the what we want to change, or I click OK, see if then it gives you another option. No, okay, that's not what I want to do. All right, I can do something else very quick, but I should do model object element type method property 2. See if it works. Ah, here it works. Okay, so let's see if I remember what I just did. Modify object element type method property. I select 2 over here. Okay. I want to change it with the panel. All right. Click OK. Now click here on shear property. Okay. And here as well. So now there's nothing over here. If you click on shear, there is no panel. So basically what we did, we changed the shear panel to become panels of thickness 2. Did you all get that? Were you able to do that? I mean, it's very, the answer is very easy. Yes or no?
Yes.
Everybody else? Yes? Okay. So here I'm just do this because I like to do it. I don't think it's rebuild. Yes. And do file, save as, or WingSpark case 2. I think we already call it that way. Save. Okay. And now what we're going to do is run it. Run here and pray. Okay. All right, here we go. We go here now to results, all results. Okay. Click F5. Deform. And here you're gonna see now that we don't have, since we don't have the shear property, we're not gonna have the one we used to use. So we need to go to plate. And let's select 7023 plate top XY shear stress. Click OK. And you can do contour if you want. Okay. Here we go. So if you remember, we're looking here at the middle at the section AA. So go here to groups and say show active group. Now you can zoom in. So you zoom in and then Control A will center. Okay, so here if you look at it, all right, I'll remove my face. Can I close this one? No, but you see basically here 25 and here an 18. So what was the result we were expecting? About 53 and 39. So if you look at it, that looks like it's about half the values, no? It's about 30, no? Times 2, and the middle will be 25 times 2 will be about 50. Okay, so what is happening here? Okay, so maybe I should have mentioned that before. So what's happening over here is what? Let's look at the units over here. So okay, so for FEMAP output. So let's see. What are the units for the shear? What are units for the shear in general? Force per area, no? Okay, so you want force per area. Okay. What are the units of the shear flow in general? What is Q? What are the units for Q? You have been doing that for a while.
So it's force over area.
No. Shear flow is what? Yeah, after I write it down, no? Force or distance. So what do you think is the relation between these two? So for example, Q should be equal to what? If you just look at the unit, it should be equal to what? To the shear times the thickness, no? So T, if you want T, so thickness, T, units will be distance, no? So if you look at, and this is something that I know that you know that, the shear flow, basically you can find the shear flow if you multiply the shear stress by the thickness. Okay, so shear stress by the thickness. Oops, I don't want to do that. I can undo this stuff here. Well, I guess I come back here. Let's go. Oh, now I don't see my face. That's perfect. But now I have zoom. What did I do here? I'm scared that if I click here, it's going to close everything. No. What? Escape, I guess. All right, is recording this stuff? Yes. Okay, so we come here. I don't know what's happening here. I don't understand what's happening. Okay, anyway. Let's come over here. So what we're going to be doing, what I'm looking here is what? This is the shear stress. So if we want to see the shear flow, what do we need to do? We need to multiply this by the thickness. Okay, what is the value of the thickness? Is 2. So what we can do is use this and do like model. I'm lucky because I wasn't sure about it. Output. Thing is process. One or more selected. Linear combination. What is the value of our thickness? Is 2. We put 2 over here, select the process. And what was the number of the plate shear stress? Was 7,023. So I'll go to 7,023. I click OK. I click OK. And now what you should see over here on results, you see this is the one from before. And now the combined output vectors, it should multiply these ones by 2. So we should get exactly the same distribution, but multiplied by 2. Okay, so let's see, F5. Okay, yeah, okay. So, all right, do this stuff over here, F5. Reselect these ones over here, the outputs. And now you see that what do we get? We get about 38 at the ends, about 51, about 51 point something in the middle. Okay, you see this is non-constant. Is growing from 37 to 51, right? And this is basically what we were getting over here, no? On the previous page. We're going from 39 to 53.78. So now we have been able to check again the hand calculation with the FEMAP. Okay, did you all get the FEMAP running? Okay, so save it. And close it. So we're not going to use it anymore. Okay, from here, maybe go, I'm going to go here to assignments. So probably next week, you're going to have the second exam, okay? So we'll be on whatever was assignment 3, and you probably have an assignment 4, no? Okay, so we'll be on assignment 3 and assignment 4. Hopefully I'm able to do this stuff Thursday. Project, here we go, project was open. So project, you see I have here some PDF file. It's also, don't expect everything to be perfect. The overall must be contained calculation type, non-handwritten document, Timoshenko, and so on. And here you have a YouTube, okay, to offset the beam address. Okay, so let's see what the project is. I always do the same. The only thing I change is the boundary conditions. One is easier than the other one. Let's see which one did you get. Okay, so you're lucky. Is the easier, is the not the easy one, but the easier one. So is the simply supported. Okay, at the 4. Okay, here be careful. It's not at the 4 corners. So change this stuff. Is along the 4 edges. Maybe let me change this stuff. Maybe here. That way I change it. Project. Okay. Oops. So boundary conditions. Simply supported along 4 edges. I'm going to put that in 4. All right. and I'm going to click save. Okay, you have no idea when it's going to be due, but we're going to make it due now. August, when is the last day of classes? So I'll make it due at the end of 30 days. Is that okay? All right, so. I think it's easier to write here. Okay, and save. Okay, so now that I know what you have here, and this shows you how to move the, okay. All right, so the whole idea is this, okay? All right, so project. So project, you have here a panel. Okay, that has here, I don't remember the shape, but let's say has stiffness, okay? So I have here the plate. And this will be here. The stiffness. Okay, so the FeedMap model. What you're going to do is you're going to model the plate using plate elements. So basically, it's the same thing we just did now on the FeedMap. Plate elements, when you think about plate, okay, basically plate, so here you will have a surface and you will provide a thickness to the surface, okay? And then model the plate using plate elements. Model the stiffeners using beams, beam elements. Okay, so what's going to happen is that once you do the model, the plate will be very easy. You do the beams over here, let's say, and you will have here 1 point. But then what happened? If you look at the figure, what you will see here will be the beams this way, so something like that. Okay, I'm kind of making it up a little bit. So what you need to do is you need to offset them. You need to offset the center of the beam.
Not to set the points instead of being already below the deco.
No, because then they will not be attached. Remember this, then you need to have the same node. So you will offset it so you have this. And this is what the video here on the notes shows. This video over here, that's what it should be showing, how to do the offset, let's see. So you see this will be the plate. And I'll show you how to do the offset. So you have the video here. I think you just need to change here the offset value. And basically, I will see what happened. It's going to create a line. It's going to move it down. I mean, let's see if I first did the first one. Okay, so let's see. Okay, so you see this one will have, you will see this, and once you offset it, it will move it down. Anyway, this is what is shown on the video, no? Okay, to know how to do. Okay, so this will be the first part. This will be to do the FEMA model. Then, what have we been doing all the time? We have been comparing analytical to FEMA, no? So this will be the way to obtain the FEMA model, and then you get the results. I don't know if they talk about stresses, deformation, and you need to find the stresses at some locations, okay? Now, analytical model. So the analytical model, the idea is very simple. We have our panel with stiffeners. Okay, I don't know why I do it this way, it doesn't matter. We do it this way. And let's say this would be T1, okay? What we'll be doing is say, okay, you know what? We have a plate with stiffeners, and what we're gonna be doing is that now I'm gonna say that this is equivalent to just a plate but this plate will be thicker because this plate now on the added thickness, I need to add the contributions of the stiffness. Okay? All right. So let's see. Now the trick or no trick over here is that from all the equations we have been using, so you need to go from here to here. So in order to go from here to here, you need to consider what is the variable, what is the most important variable for you to model, okay? In order to get the equivalent. So let's say over here, let's go over here to models. And go to sign equations. Okay. If you look, why can I go down? Okay. If you look at this equation here for the stresses, okay, let's look at the stresses. What do you think is the most important quantity over here to properly model? I mean, the moments are going to, the loads are going to be the same on the FEMAP that will be on the analytical, correct? So what is the other variable for which everything is in function of? The moments of inertia. So basically what you need to make here sure, in order to go from here to here, you need to say, let's say the I of the model needs to be equal to the I analytical. So if you look at it, this is A and this is B. What would be the moment of the inertia of the I analytical? Will be equal to what? I mean, I just do like if it was a rectangle here, okay, would be 1/12 of A T to Q plus whatever you do with this side. Okay, you can find what is this stuff. Now, the I of the model, okay, you need to do what? Kind of something we did before, add plate plus I stiffness, no? You equate these two. You equate these two, solve for T2, and you will find it. So I'm not gonna do it for you, but maybe let me show you here. It's something that we're gonna do later, but since I give it to you in advance, let's see, maybe I can show it to you here. E418. How can I go back? Okay. All right, here we go. Let's say summer 24, doesn't matter. Lectures. Johnny, this is by the end, let's say 17. No. 18. Yeah, there we go. Structure idealization, okay? So you see, this is kind of what I'm just doing now for the project. Something equivalent. The important variable is the I. And let's say over here, you need to go from this vertical member to this one. Here, I do the effect with just the vertical member. What is the I of this vertical member? We do 1/12 of T, the base, times the height, H cubed. I want to model this one. If I do this one, this would be what? I equal to B1. So B1, Y1 squared plus B2, Y2 squared, but B are the same. So do 2B1. And I find for these two B's to be equal, one needs to be the equivalent area. I found over here the equivalent area. In this case, you can do the same thing, but let's say you know the B's, you can solve for T. So it will be kind of the same process. So I'm keeping all this stuff on the video. So it's basically kind of the same idea. All right, and we'll be doing that later. I'll put it over here. And so on. So the projects, you need to do that. And then what's going to happen is what? Let's say assignments. You're going to find your equivalent plates, simply supported plates. You have a thickness. A and B will be the same. The only thing that's going to change is the thickness. Then you will come here to the project. You will open this file, or you don't have to use this book, but this is the most classic. This is the guy that, okay, so you said download if you want. Okay, so I don't know why. Okay, you go to Timoshenko, this book, basically. It's an old book. This is a guy, he's the father of solid mechanics, at least in the United States. And you can come here and look at maybe simply supported plates. So pure bending of plates, slope, symmetrical bending of circular plates, small deflection, simply supported rectangular plates, simply supported rectangular plates under sinusoidal loading. Simply supported plates under hydrostatic pressure, so 124. Again, now I did not mention, but what is the load on our plate is a uniform pressure. So you will go to page 124. Over here, I know what 124 is. Oh, it's article 124. I think it's article 124. So let's see which article is this one. Maybe it's page 124, I don't know. I mean, look how lucky you are to do finite elements. Look what would be to do the analytical solution, okay? So it's page 124, simply supported plate under hydrostatic pressure. So this will be the expression. This will be the expression. Do you like that expression? Okay. This will be the expression for the deformation, but obviously they simplify it for you. So the maximum deformation is at the middle of the plate, is given by this expression. Okay. So now you can look at the deformation of the finite element. Look at the deformation using this equation here. So basically you need to do a little bit of, all this stuff is to teach you how to do a bit of research, no? Or to study on your own. This is not like something you're gonna get straight from the notes. And you're gonna have to do a little bit more work to find the stresses, okay? But basically everything is on the book. All right, you need to do a little bit of research over here. Okay? So tomorrow I want you to spend time, because I won't be here in class, to work on the project. Is that okay? Do you have any question for me?